Hi, everyone. The following discussion will be on a topic started here at Microsoft as a feature for Video Indexer for recognizing animated characters in a video. And later, we took it into an academic paper to be presented in a Eurographics conference next month. The following work is collaboration with Gal Rappaport and Ariel Shamir from Reichman University. And as mentioned, what started as a video indexer project, and two patents were issued on this work, and I even had the chance to present some of this work about 2 years ago here at the Bond. I think it was next to MLED's conference where this also was mentioned as part of the Distinguished Contribution Award on the conference. As Rachel mentioned, I'm on a PhD program now, and this work was kind of a pivot towards an academic work, where in this session I'll go through the motivation, prior art, some learning theory to have everyone on board with the technology, the method itself, and later application, discussion, and demo. So stay with us for the demo. It's kind of cool. And this is why the work is formalized as an academic paper for the outline. So as a motivation, why do we need to tackle animation in media? So as a $250 billion market, not including gaming and other related domains, this is quite a massive industry to tackle in the context of an Azure service. And while we were back at the time contacting with media companies in order to better understand their use cases around this domain, we've highlighted 4 different use cases that could empower media companies to use such a technology. The first was IP protection on social media, both to keep our brand safe as a media company and to see trends in the network. Gender bias monitoring. So all sorts of biases are monitored by media companies, which are not the studios. The studios have the script itself, right? They know more or less where each character has appeared, but media companies gets the final product and distribute it across their network. So nowadays, gender bias is a prominent issue to tackle, and labeling manually on the timeline which character appeared exactly in the frame level accuracy is not feasible. Also helping media companies produce highlights video or monetize their content for third parties. So one may ask why animation is hard, right? So if we have some cartoon character like Cosmo, this is Cosmo, has a discrete number of colors and pretty simplistic outline. So why is it so challenging to capture Cosmo through video, right? With AI, simple AI or whatever. So sorry for this poor visualization, but I wanted to fast forward a short clip of Cosmo changing shapes. And you can see here the sampled frames from this short video, where none of these characters look exactly like Cosmo, right? We have a fork, a key, a fish, a toaster, and all sorts of funny shapes, and the variability within a single character is pretty intense. On the other hand, we can see the variability across different characters, styles, and animation technologies. So in terms of styles, we have here some examples from CGI, manga, cutout, which is the South Park technology, and even black and white Popeye legacy animation. So both types of variants makes it very challenging to capture where exactly every character has appeared in some latent semantic space. Another challenging task is multi-object tracking, the ability to track across a single shot all objects, or in this case, pedestrians. And here we can see the state-of-the-art model nowadays, which is called the PyTrack. And it does pretty stunning work on tracking pedestrians. This is a task that was heavily studied and is funded by many agencies. And there's lots of labeled data in a frame label accuracy to train deep neural networks to accomplish this task. If we'll take this state-of-the-art algorithm and apply it to animation, in this case, Bob the Builder, we can see some of the characters are captured, but trucks are no doubt not part of this set, and we want to be able to capture those as well. And some human characters are not captured as well. But if we'll take a different animation technology, like this one, we can see that none of the character was recognized by this state-of-the-art algorithm. And since generating or labeling a data set for animation is costly and not available at the moment, we later on tried to take a different approach on the multi-object tracking. So in terms of prior art, the main paper on which we compared with was a paper by Sumandepalli et al. From 2018. They essentially tried to take a full feature film, animation film, and recognize all the characters in the video, not by name, but to give some, what they call a dictionary, like the cast, which we try to take, and optimally having a single image or exemplar, as they call it, per character. In this example, we can see that some of the characters have been captured multiple times, which is unwanted, and we want to do better than that. And they quantified their results and published a data set called the SAIL AMCD with 46 training videos and 8 test videos. Their general approach was to sample every 10th frame, apply an object detector called multi-box, and apply some logic that filters examples from using a saliency map. Later on, they applied a single object tracker to do something different than what we will later do. It's a different approach, but they took a single object tracker in order to throw away examples which are redundant. Later on, they've applied 2 types of embeddings to represent some similarity space in a latent space using AlexNet FC7 layer, which has 4096 dimensions, and applied affinity propagation clustering in order to group all bounding boxes in the latent semantic space and have one example from each being the exemplar from this cluster. And finally, they give this set as their dictionary. Later on, another nice work by Lee et al. From 2020 have copied the entire pipeline, but focused at doing the detection better. So instead of the multi-box by the previous work, they've suggested a new architecture to adapt the domain, to be agnostic as possible for the domain, as the different animation styles have very different characteristics. They've applied their work on top of a CVPR paper that does exactly that on objects. And what was not perfect here, in my opinion, was that they published the results on their own data set, which was not published. And their comparison to the previous work by Samandapalli et al. Was somewhat cherry-picked. They did not give their results per the entire test set, only a few examples that were sampled from the training set and test set. So we essentially compared to the work from 2018. Any questions before we continue?
So no studio has published a dataset because they know the script and maybe they can just give you the characters.
Right, but they need to know exactly what you want to do. So we worked with bounding boxes and they might say we want to do semantic segmentation or instance segmentation, or there are many tasks that could be performed on such data. And yeah, it's a rather novel area to work on, and there's no studio that published their work. But what we did is and I'll talk about it in a second, we built our own data set. We reached out, it has 3 parts. The first part was based on a collaboration with design partners, where we asked them to share with us data and we labeled it. Self-supervision is, sorry, but I'll read it from the text, replaces the human annotation block by exploiting some property of the data to set up pseudo-supervised task called a pretext task. So it employs some task that we have some prior knowledge on the data and helps us train the data and initialize the representation in the model of some latent semantic space in order to later conduct fine-tuning or apply the training algorithm on top of a different task, optimized for some challenge which we don't have much labeled data on. So let's see some examples. For instance, one example of a pretext task is to predict the rotation of an image. So we can have some data set, it could be ImageNet, for instance, and we want to rotate images on a random angle and let the network infer that angle. That way we can train an algorithm to learn the basic content of natural images, and later on learn it into a different task, a downstream task also called. Another example is to split the image into 9 patches and give the model the center image, let's say the face of the eyes and nose, in that case the center of the cat's face, and then sample one of the other 8 patches and let it infer the label of that patch. Again, that way the network learns some structure of natural images. Another example is in painting. I can take an image and crop some bounding box and let the model repaint that area. It could also be image coloring, which is also an interesting task. And guys from Google has applied such a work on videos as well. They give it a reference color image and black and white video. And the network can learn to track objects and even do pose estimation only by learning the reference color image and applied in a coloring task on the black and white video. One last concept I want to address here is triplet loss, which is part of a wider area called contrastive learning. Triplet loss was suggested by folks from Google in 2015, and it basically encodes a latent space in which, given 3 examples, 2 of which are having the same label and a third which have a different label, it could be the identity of a person's face. We can ask the network or formalize the loss function here to have the two examples belong to the same label be closer in the latent space by some margin than the other label. Those examples are referred to as anchor and a positive for the same label and a negative for the different label. So our method, we call it casts, and it looks as follows. Try to keep that in mind in general as we will go over the different boxes here. So we take a video. It could be a full feature film or some episode of some animated series. We apply a basic algorithm to do shot segmentation. So we know in a frame level, the split into different shots across the video. Later, we sample examples across those frames and apply character detector using YOLO v2 to classify one of 2 classes, whether it's an animated character or not. Since it is a pipeline, we can only throw away examples in this approach, and therefore this detector is trained for recall orientation. After that, we apply a multi-object tracker to track per a single shot the trajectory of each of the characters in it. From these tracklets, we later sample triplets, and this is the main hypothesis of the paper. We basically assume that 2 examples belong to the same tracklet could be anchor and positive in the triplets notation. And if we have a different bounding box on the same frame as the anchor bounding box, then we can assume it's a different character. So we consider it as the negative example. Afterwards, we fine-tune this embedding, or should I say, we have our own trained embeddings over a wide range of animations, and here we apply a fine-tune additional 10 epochs to refine the network to this specific style. And using this network, we can now use it as a semantic embedding with semantic latent space to be able to compare the identity of different characters in this video. Any questions before I continue? We'll go over all of them. Okay. So the shot segmentation applies a simplistic approach from 2004, tracking the entire frames, color histogram change, and looks for both abrupt change or gradual change of the camera in order to say, okay, here starts a new shot. In order to train 2 in the wild models, that would be the detector itself and an embedding network. We've built 3 datasets or a single dataset with 3 splits. The training was taken from, not taken, but contributed by partners of Microsoft, which we've labeled ourselves, given both the bounding box of each and every sampled frame with then its name. So we can use it both for training the detector without the name and also the embeddings as a multi-class classification task. The test set was taken from YouTube, having pretty challenging examples from amateurs and other freely available content. And the third data set was the evaluation data set, is 7 series. Each has its own style, more or less. And each series has 2 episodes, being a training episode and a test episode. So we can later see how we can run a pipeline on a training episode, learn something, and apply the model on a different episode to generalize on different images altogether. Yes.
Question. Do you retrain the entire pipeline for every piece of content, for every media?
In the fine-tune, you mean? The last component?
I mean everything, like the character detection, everything. Is it retrained, or do you have some fine-tuning, some global model that you fine-tune per style?
Okay, so good question. In terms of the detector, we only train it once on a variety of styles, and it is working in the wild. We do not fine-tune it later. Okay. It was taken. We tried faster RCNN, and it worked not as good as YOLO v2, so we used YOLO v2, and here we tried 3 different approaches. The first being the vanilla object detector using different labels like person, animal, doll, toy, stuff like that. And as far as we got was less than 50% average precision on this task. So later we tried to take a person detector that was trained here at Microsoft over additional data, and it performed more or less as good or as bad. And then we fine-tuned this model on the training set, our own training set. And this is what we got on the test set, which was rather challenging. That's why the average precision is not perfect. But we have a significant boost in performance over animation due to that. So this piece works in the wild, meaning that we only train it once and we use it on all styles, and then we do not fine-tune it. Does it answer your question?
Yes.
The second piece is the embeddings. The embeddings is a network that we use to, we trunk the final piece of the classification layer, having some multidimensional vector that can represent an image or the identity, hopefully, of an animated character in some latent semantic space that will show us some similarity between examples of the same video, examples of the same character in a video, rather than other characters in that same video. So here we tried 3 different backbones. The first was ArtMiner, which is a work that was conducted on art objects, and also ResNet 18 and SE ResNext, which was an improvement of, so there's ResNet, which takes the residuals in order to do better inferencing. And after that, someone suggested ResNext, which employs some features from the inception layer. And this is also a later approach that also added some additional concepts to do better image classification. So we used this, and this was found to have the best results. Here we can see a comparison of over the test set where we've basically used the embeddings in order to represent each of the bounding boxes, and we sampled tuples where tuples could have the same ID, the ID of the animated character or not. And we've run a cosine similarity on those. We ranked this array, or sorted this array, and this is how those raw curves are shown in a binary classification approach, although it's a multi-class classification. Here we can see that our refinement of over 40 epochs over the SERES next backbone has suggested the best results. An additional test we've conducted to do, as we want to do a clustering later on, we said, okay, we can test how well these clustering results are given this backbone, the use of selection of backbone. So we've sampled 6 sets, each have a different set of characters. And you can see here, it's a bit small, sorry, but you can see the purity on the y-axis, and the x-axis is the number of clusters, where the vertical red line indicates the true number of clusters. So we can see here that across the board, usually the brown and purple representations give the highest purity, which is what we want for any value of k, the number of clusters. Multi-object tracking, again, is a task to track each and every example of the same object in some short video. I used a paper from CVPR 2008 by Zhang et al., which took a rather classic approach of optimization and formalize it as a network flow, or max flow mean cost. And in a nutshell, that was conducted since we did not have enough training data that could fit a frame level representation of a tracking algorithm to be fine-tuned and transfer learned from a task like PyTracker, which I've shown before. And this approach formalizes, like the classic max flow min cut algorithm, a source and target nodes, which are linked into each and every bounding box. Each bounding box is split into 2 nodes here, an entry node and exit node, where if, for instance, in some frame, which is not the first, we get a flow coming from the source into some particular frame, which is not the start, then we know that some character probably appeared somewhere within the shot, like birth and death events in the tracking task. The red edges are weighted with respect to the detection confidence, and we have also the blue edges, which have some cost, which considers several metrics that we've suggested. That would be the semantic similarity of the embeddings, So those blue edge weights are essentially the match probability between two consecutive frames and two specific bounding boxes within those frames. So we want to measure how probable is to link those two bounding boxes. So we took into consideration the semantic similarity given our pre-trained embeddings, the IOU between those frames in the IOU between those bounding boxes in those frames. Sorry, the distance between them, the angular velocity, or should I say, if two examples are far away, they should be small, and those bounding boxes could not. Some character is less probable to do far translation on the frame given a brief time difference. So this would be discouraged by the cost function. And additional examples for changes in the box size and time decay for skip connections. I won't go further details on how Dave came up with the idea of taking the map representation into linear programming, but this is very elegant idea, and in just a few words, I can say that there's a mathematical magic here that since the representation of the LP relaxation here constructs a matrix in which each entry is an integer, we can essentially solve the relax problem and get an integer solution in terms of flow, and as we cannot have some partial flow function as a result of this algorithm, and yet since this matrix is totally unimodular, we get an integer solution, which is very nice in my opinion. And the formalization as an LP problem takes the topology of the network into the objective function, which we want to minimize. And we want to find the best Fij, meaning the flow function, which minimizes the cost function under those constraints, which have a unit capacity for each edge, as the link between two consecutive bounding boxes should be 0 or 1. And the other constraints are straightforward for flow conservation and other constraints. For those of you who know LP representation of network problems. And in a nutshell, essentially, it is solved with SciPy if you use the sparse representation for these matrices, because they can get rather big, and it's very cool. And what we get from that is a flow function that we can retrieve easily with fastest path algorithm, shortest path algorithm, sorry. The set of trajectories we think are most probable. From them, we can sample those triplets and refine the representation. Here we can see 4 examples for triplets. A trivial one indicates this positive and anchor examples of this red character, and the negative was rather different. Those make the most of the examples in the by the algorithm. We can also retrieve some non-trivial examples like Cosmo changing its shape, and still we can infer a good representation that will aggregate those examples together in the latent semantic space due to this capability. Two side effects here are examples which have not the same character. This purple character is not identical, but yet we ask the network with the loss function to put them closer in the latent semantic space, far closer together than this example, the third one below, which is okay. We still learn from that. Another example from that is capturing non-characters as character, and that is okay. And never there yet. We ask the network to put those ducks together closer than this object. Here we can see Flugels, a different animation, where we can see how the self-supervision takes the clusters to be more concise and could be easily separated with a linear classifier. Any questions before we continue?
What is the scope of the graph you showed before? It's a single frame or all the movie? Like
Here?
No, the graph that tracks the character.
The scope, we take each shot and apply the multi-object tracking on a shot. Because if the shot changes, then we have new locations across the spatial domain, and we don't know whether a bounding box that was in this location earlier is the same character or not. So the hypothesis holds only for a single shot.
Okay.
So some applications. Clustering, here we using the embedding space we use, we encode the identity of the characters into 2048 dimensional vector. We apply some deduplication process. I won't go into details. And we selected the DBScan algorithm for two main reasons. First is non-parametric, and we don't know the number of animated characters in a video. And on top of that, their frequency is rather long tail. So it's a very challenging clustering problem to solve. And it can identify examples as noise given the distribution on the latent semantic space, which is something we wanted since, as I mentioned before, the pipeline is recall oriented at its beginning, and the clustering can throw away examples which are rather noisy at its end. So this is like giving the pipeline at its end being more precision oriented. Here we can see the effect of the self-supervision on clustering. We can see that for the same data set across our evaluation data set, we get less clusters to represent more characters. And on top of that, 90% of the characters of the clusters are totally pure, which is something that we want. And the overall number of labeled bounding boxes, given that we label those clusters, is 50% larger.
So, and this analysis you do for the whole video, right? Like you aggregate them.
Right.
You assume that the same representations for a shot will be the same for
per episode, a full analysis, and this is an aggregation across the entire data set.
Yeah.
Another test we've conducted is to estimate the silhouette gain. Silhouette is a metric to quantify the goodness of a clustering solution on its semantic space without having labels on those examples. So we can see that the silhouette is significantly better, higher, using self-supervision. with p-value of less than 0.5%. And at the end, all of these examples were clustered together in the same cluster without any other character in it. And when we compare it over the stale MCD dataset from 2018, we can see that we get overall much better results. The work by Samandepalli et al. Have suggested those metrics. One of them was the median number of exemplars per character. So the optimal is 1, and here we can see that they got 3, and we got much lower value, which is very much wanted. Here we can see an example of the characters collected from Cars 2 by our algorithm. We can see that we have two examples of Lightning McQueen, the red car, but the rest is pretty solid. While the work from 2018 has 6 examples of Lightning McQueen and more examples that indicate not as good results. South Park is another example taken from our dataset. Here we can see failures like this tree here that was captured as an animated character. And we have Cartman appears here on one costume, here on a different costume. And here below, there's another example of Cartman, but overall, the results are very satisfying, having long tail characters as well as main characters captured pretty well. On our data set, when we try to quantify the effort required from a labeler, because one of the benefits of using that is that we can generate lots of training label data by labeling only clusters and not the entire data set, which is tedious. And we can see here that using very low effort, we can label quite a massive data set using this method. While we've done that, we've trained image classifiers after running this pipeline over training episode in the evaluation dataset and tested upon the test episode in the same dataset. Here we can see that overall the series used here is Bob the Builder, Fireman Sam, and others have reached almost 89% F1 score by only labeling the clusters and not the entire data set per bounding box. One final application is conducting a full labeling per frame. This way we can get to know exactly where each and every character appeared at in the frame level, and we can estimate the gender bias. For instance, we applied that on Cars 2 and found that female characters gets only 22% of the screen time, which is not good. Shai, you have 2 daughters. What do you think about that?
I will talk to Disney about this.
So some points for discussion. We found that the detector has some bias for hands and feet. And those examples were considered as non-characters and were not labeled. And those are some of the errors we see in the confusion matrices. So if you ask yourself what makes a talking tree different than a background tree, it's probably these attributes, facial attributes, hands and feet, etc. Another example was it's easy to see here on the Fireman Sam series that if we have a set of characters within this series which were uniform, then our approach to capture the entire body as the unit of analysis is sometimes suboptimal, as some of the characters here look very similar, while what makes them different is their faces, and we're not focusing on only faces here. So this is one of the limitations that could be taken further for further work. Another analysis we've conducted was on the question whether to consider the image classifier that we train later to be labeled per cluster or per character. So those two actual clusters that were taken from the results are two clusters of Bob the Builder, Bob. So we can consider to label Bob in both of them as Bob on the left, or give them the idea of the cluster being Bob1 and Bob2, train an image classifier and trunk the number on the inference later. So we found that the first approach of labeling each cluster with its character name gives significantly better F1 score. So other limitations are we train in a supervised fashion an initial two models to be worked as in the while approach, meaning the detector and the baseline embeddings. As I mentioned, there's been work in this cascade pipeline. If detections are misdetected at the beginning of the video, then there could not be recovered. And we have some ideas how to take the temporal information further into the analysis and conduct smoothing. And I want to show you a demo of Flugel's video, a different style. Here we can see that our image classifier that was trained on the training episode was applied per frame on this clip. And since it was applied per frame, it's kind of noisy. The bounding box jumps around as it is no smoothing is applied here. Some credits for the media companies owning this media pieces here. And with that, we can get to some questions if someone has anything to ask. Good. Anything from the crowd?
Hey, maybe I missed something, but in the last video, how did you retrain the model on those two characters? Like, what was the base data set? You just bring them some pictures?
Yeah, so we have labeled. This is the data we worked with. It was split into training that was used to train the in the wild models, the test to estimate their performance. It could sometimes they refer to a validation set. It's more used, and the evaluation set is built differently. We have 7 styles, 7 series. Each have 2 episodes. First was used as a training episode on which we applied our pipeline. And the second was used for testing. how we've conducted that. So after we ran the pipeline on, for instance, Bob the Builder, the training episode, then we took all of the labeled examples that were labeled in a cluster level, trained as is as an image classifier, and later on inference time, on the test episode, we sampled all frames. We applied the detector on all of these frames, and each bounding box was cropped and inferred with the image classifier that was trained on the training episode for the label of this bounding box, meaning the name of the character. Does it answer your question?
Yeah, I think so. Thank you. That was really, really nice.
Thanks. Okay, so with that, I think we can conclude. We have 5 minutes to spare.
Thank you, Oron.
Thanks for listening.